a satellite is passing by, and the satellite is monitoring the area that we see. The satellite will see the white surface, and it could deduce how concentrated the ice is in this region. So the satellite could easily measure ice concentration together with some uncertainty. But the satellite cannot observe what would be the thickness of the ice, at least with the technology that it has on board. But at the same time, it's possible to also simulate what would be the ice concentration in this area, and we could do this with a model. And the advantage of the model is that it can also simulate sea ice thickness. So the model could simulate at the same time ice concentration in this region and at this time, but also sea ice thickness. Now, data simulation is truly the operation to update the estimate that we have of sea ice concentration and sea ice thickness from the model, to update this information as to get a new estimate that takes into account the observation that we had from the satellite, and to return a new estimate of the ice thickness with less uncertainty and which is closer to reality. Now, how powerful is this data simulation technique? Well, let's look here at two retrospective forecasts that were carried out in September 2007. The figure that you can see on the top is the September 2007 sea ice cover that would have been obtained without data simulation. And the bottom one is obtained by prescribing improved initial conditions in March. And in fact, if we go back in time and we look at sea ice thickness in March, so in the preceding winter, then we do see some differences in ice thickness, as I told you earlier, that can explain the differences in September sea ice concentration. And what I think is really fascinating here is that no observational data of sea ice thickness had to be used at all. So the only difference between the bottom line and the upper line is that on the bottom line we fed the model with observations of ice concentration that help to better estimate sea ice thickness and then deliver better forecasts in September. So this is the first demonstration that data simulation can be relevant at the poles, because the top forecast, for example, the forecast on the top, would have said that the Arctic Ocean could have been navigable in 2007, whereas in reality this was not the case at all. Now, the second question that I mentioned was about the increase of Antarctic sea ice, and to try to understand whether the increase in area was accompanied by an increase in the ice volume. And exactly the same technique was applied to Antarctic sea ice, but on a much longer time scale, and so in the Antarctic, to reconstruct sea ice thickness. And the main conclusion from this study was that, again, data simulation could be really helpful to understand the past variations of sea ice thickness, and it confirmed that the observed increase in sea ice area that we saw from satellites wasn't just an accident, but that sea ice also has gotten thicker and thicker in the Ross Sea and in the Weddell Sea, and it's gotten thinner and thinner in the Amundsen and in the Bering Seas. The very important message here is that these results suggest that what we observe from space about the expansion of Antarctic sea ice isn't just chance. There is really a sign that the total mass of Antarctic sea ice is increasing, and that this could be caused by a true mechanism that is contributing to expand the volume of the ice. For the very last question that I was mentioning, the question about model parameters and how to calibrate those parameters, I have to tell you a quick story. And the story dates back from 2009. I was a student in engineering at that time, and I was finishing my studies, and we had to design a system to stabilize the level of water in a bucket. So the bucket that is shown on the figure, we had to stabilize the level of water, but the bucket was leaking. So we had to somehow control the flow of the water through the tap to keep water at a steady level. Now the problem was quite complicated, and we started exchanging our MATLAB codes with other groups, because this is how you do when you don't have a solution and you're a student. And this is what the code of one of the group looked like. It's a set of instructions that we are all used to give to computers. But at some point, there was a parameter that was called alpha. And after looking into detail in the code, it turned out that alpha was purely an unphysical parameter, so it had really no physical meaning. And this parameter alpha was there to be just adjusted and to conveniently solve the problem. So if you could find the right value for alpha, then you could solve your problem. I'm telling this story because in CIS models, there are a lot of parameters that look like this alpha parameter. One of these parameters is called P star, and some of you may know what this parameter is for. It's a parameter that defines how strong or how compressed the ice could be. And truly, this is a parameter that has hardly no physical meaning. And it's mainly used to tune our models. And on the right, you can see the relationship between this parameter on the x-axis, so this parameter P star, with some variable of the model that we can observe. So you see that there is a negative relationship between the parameter and the speed of sea ice at one grid point. And the idea here is that data assimilation also can help. If we have some observation of ice speed at the grid point that I'm mentioning for that day, suppose that the ice speed is around 0.1 meter per second, then we know that the value of the parameter that we should use should be around 1 to 10 to the 4 rather than 4 10 to the 4 Newton per square meter. So data assimilation can be applied to extend the problem of estimating the state of a system to estimate the parameters of a system. And this is what I did. What the problem with the model that we were using is that this model was simulating on average